Hello my friends. Alright, excellent. We already did the essentials with data preprocessing by importing the libraries and importing the dataset. And now I'd like us to particularly focus on this feature scaling that we're about to do. So I've already taught you feature scaling in the data preprocessing part, part 1, where indeed we implemented together this feature scaling tool at the very end, feature scaling, where we learned how to scale with standardization the training set and the test set separately. Okay, so that's what we did. Now we are in a slightly different situation in the sense that indeed we do not have a split of the data set between a training set and a test set. And that, I remind, is because we want to leverage the maximum data in order to learn the correlations between the position levels and the salaries. So the first thing is we will actually apply exceptionally feature scaling on the whole matrix of features X. Then the second important point and the second difference with what I taught you before in this same data preprocessing tools implementation is the fact that in this situation we only applied feature scaling to the features, right? We only applied feature scaling to xtrain and xtest, which are the features of respectively the training set and the test set. And we did not apply feature scaling to the dependent variable vector y. But why was that? Why didn't we apply here feature scaling to the dependent variable vector y? Well, that's because remember, the data set for our data preprocessing tools implementation was a data set where the dependent variable was taking values 0 or 1, right? We can scroll up to have a look again. Remember, these were the purchased decisions of this retail company, and that's the dependent variable taking the following values: 0 for the customer didn't buy the product, and 1, the customer bought the product. And therefore, since it took value 0 or 1, then we did not have to apply feature scaling here, because exactly same as the dummy variables here, the values 0 and 1 are already in the same range as the one resulting from applying feature scaling onto the features. All right? But now we are in a different situation. Indeed, this is our new dataset, position salaries, where the features are indeed the levels going from 1 to 10, and the dependent variable taking values from 45,000 to 1 million. And so now I have a question for you, and after answering this question you will know what to do in any feature scaling situation. So according to you, do we have to apply feature scaling to this dependent variable, the salary? And the answer is, well, yes. I'm sure you guessed that right. Indeed, we have to apply feature scaling because same, we don't want this feature, which takes values much lower than the values of the dependent variable, to be neglected by the SVR model. And that even if there is not an explicit equation, like in multiple linear regression, this is an explicit equation because y is explicitly resulting from a linear combination of the features, and for our SVR model this is not the case. We have an implicit equation, but still through this implicit equation, well, if the salary is way higher than the features, and here this is absolutely the case, well, accordingly the feature might be neglected by the model. And actually I of course tried to build this SVR model without applying feature scaling, and you can check that this absolutely doesn't work. Indeed, if we don't apply feature scaling for our SVR implementation and training on this dataset, well, you will see that the SVR model will not work at all. So we have to apply feature scaling here on both the feature, where the values go from 1 to 10, and the dependent variable taking values from 45,000 to 1 million. All right, and so now you know everything about feature scaling. You know what to do in any situation. You know that you don't apply feature scaling to some dummy variables resulting from one hot encoding. You know that when a dependent variable takes binary values like 0 and 1, you don't have to apply feature scaling either because the values are already in the right range. You also know that when the dependent variable takes super high values with respect to the other features, then you have to apply feature scaling to put all the features and the dependent variable in the same range. And finally, you also know that whenever you want to split your dataset into the training set and the test set, well, you have to apply feature scaling after the split. All right, so now you know everything about feature scaling, and By the end of this implementation, you will also know something very important to do with feature scaling, but on the practical side, which will be the inverse transformation of feature scaling. When you scale your features or your dependent variable, at some point, to get the final prediction and to visualize the results, you need to inverse that feature scaling, inverse that transformation to go back to the original scale. And I will, of course, teach you how to do it so that we can not only get a very relevant prediction at the end in this step here, and also a super nice visualization where indeed we have the x-axis and the y-axis back in their original scale. These scales of the levels going from 1 to 10, and this scale of the salaries going from 45,000 to 1 million. All right, so you will know everything, and now let's implement this new step, feature scaling. But just before, since we're going to apply a lot of transformations on both x and y, well, we're going to do some print to see the before and after the transformation. All right, so let's create two new code cells here. Let's first do a print of the matrix of features x, then a print of the dependent variable vector y. Now we're going to run the cell to print x, and x contains, of course, in a 2D array, as you can see with a double pair of square brackets, all the position levels going from 1 to 10, so that was totally expected. Then let's print y, which will this time contain in a one-dimensional vector all the salaries corresponding to these position levels, so all good there. But now we will have to do a first transformation, and I'm not even talking about feature scaling. That first transformation will be to reshape this y into actually an array, a two-dimensional array where you have the salaries displayed vertically. Meaning that instead of having, a horizontal vector of the salaries here, well, we want to have the salaries vertically in a two-dimensional array. And so now the question is, why do we want y to have such a format, in the 2D array? Well, that's because, the standard scaler class that will perform standardization, meaning feature scaling, expects one unique format in its input, when you apply the fit transform method, which is a 2D array. If you input here a one-dimensional vector like what we have here, this will return an error, simply because, well, this standard scaler class expects a 2D array as its input. So now we just have to transform this into a 2D array, and you actually know exactly how to do that because we already did it. I'll give you a hint, this was in the multiple linear regression section. And so now, well, of course, I would like you to press pause on this video and try to transform y, or reshape y into this 2D array with the salaries displayed vertically. All right, so please press pause, and now I'm going to give you the solution. All right, so we're going to create a new code cell to do this. And so, well, first we want to update y, and therefore, we will start with this, y equals, and then we'll do the necessary transformation to return this new y. And so how do we do this? So the first thing to do is to take y again, from which we're going to call that reshape function, into which we're going to input, well, the new shape that we would like y to have. And remember how we have to enter this new shape? Well, we have to input here two elements. The first one being the number of rows of this new y, this new format of y we want to have, and then the number of columns. So that's easy, since we want to have the salaries displayed vertically, in different rows actually. Well, what we want to have for the number of rows is, of course, len of y, the length of y, meaning the number of elements in y, meaning the number of salaries, okay? So that's the number of rows, and then the second element here is the number of columns. And of course, we want one column because we want to display the salaries vertically in a 2D array, of course, and therefore here we input 1, as in one column. So we're going to have, actually, since we have 10 salaries, we're going to have 10 rows and one column. Okay, so it was good to do it again. Now you become more familiar with this reshape trick. Okay, and now of course we're going to print this to see and to check that everything's all right, and mostly that we have the right format expected by this standard scale class, which we'll use then to apply feature scaling. So there we go, print y, and let's first execute this to reshape y, and now let's print y to indeed check two things. That first we have a 2D array, we can clearly see that with the double pair of square brackets, and also the salaries displayed vertically, just like this matrix of features, which is also a 2D array, of course. Alright, so now everything's perfect. We're ready to apply feature scaling, and so we're going to do that right away, starting by creating a new code cell here. Alright, so now how are we going to do this efficiently? We always want to be efficient when we code, so of course we're going to grab our tool in our data preprocessing toolkit. I'm talking of course about the feature scaling tool, and we'll have to adapt this a bit because this was applied on the training and test sets, but no worries, we will adapt it very quickly and efficiently. So I'm copying this and I'm pasting that right here. And now, of course, I would like you to please press pause again and try to figure out on your own what we have to modify here to make this feature scaling work for our situation. All right, so pause, and now let me give you the solution. All right, so first we don't have a training set or test set here, so I'm going to remove this line of code. I'm going to, remove that as well, all the index selections and here as well, and I'm just keeping X, and then let's see what we have to do. All right, so first that's already more clean. Now, with what we have here, these 3 lines of code, we are indeed applying feature scaling to the matrix of features X, which is one of the things we have to do indeed. That's good. However, as we've just explained, we also have to scale the dependent variable vector, the salaries. And of course, and that's the important thing you had to understand and figure out, we're not going to use the same standard scalar object on both the matrix of features X and the dependent variable vector Y. Why is that? That's because, when you fit your object SC on your data, well, it is going to compute the mean and the standard deviation of that same variable, and therefore, since of course we don't have the same mean and same standard deviation for our levels here and our salaries, well, obviously we have to create 2 standard scalar objects, one that will be fitted to X in order to compute the mean and standard deviation of the position levels, and one that will be fitted to Y to indeed compute the mean and the standard deviation of the salaries. All right, so that was the only important thing to understand. And therefore here, I'm actually going to call this SC object SCX in order to say that it's the scalar of the matrix of features X, and here SCX as well. And now I'm going to create a new standard scalar object, the one that will be used on our dependent variable vector Y, and therefore here I'm replacing SCX by, we're going to call it SCY, so that it's perfectly clear that this is the scalar of X and this is the scalar of Y. And now we're going to copy this, paste that right below, and here we'll just have 3 little replacements to do, which are first replacing X here by Y, then SCX here by SCY, and X here by Y. So that now we're ready to scale both our matrix of features X and our dependent variable vector Y. Let's check it out. Let's run this cell, and now we're going to add 2 new code cells to print the new X and the new Y and see what they have become. All right, so 2 new code cells, and let's start here with a print of X, good, and then a print of Y, and now let's run these 2 cells here, starting with print X, and indeed, well, we have some perfectly scaled values of the position levels going from minus 1.5, and that corresponds of course to position level number 1, and 1.56, which corresponds to position level number 10. All right, and now let's print Y, and this will be interesting. Here the values will go from minus 0.7, which corresponds of course to the salary of $45,000 per year, and 2.64, which corresponds to the $1 million salary. And as you can see here, this time the values are in the range from -1 to +3. That's why in the data preprocessing part, I told you that usually standardization transform your values between -3 and +3. All right, so there you go. Congratulations. Now you successfully applied feature scaling for the SVR model, and especially for this data set where clearly feature scaling had to be applied on the dependent variable. And now I'm really glad for you because you now know how to handle any situation of feature scaling. You just need to know how to inverse the transformation, but that will come very quickly because then we will actually train the SVR model on the whole data set. And then when we get our smart model after the training, well, we will predict that salary of the position level number 6.5, and that's where you will learn how to inverse the transformation. All right, so I can't wait. Let's build and train first the SVR model on the whole data set, and then we'll get together the final result. And until then, enjoy machine learning.